Click on the link in the lab write-up and you should go to a simulation called the ramp. It can take a little bit of time to start up depending on your internet connection. Set up for the filing cabinet. Make the angle of the ramp 0 using the ramp angle slider and position the filing cabinet all the way to the right using the position slider. Make sure to write down the coefficient of friction for the filing cabinet and the other objects that will be used in the data table. Notice the coefficient of friction for the filing cabinet is 0.3, 0.5 for the refrigerator, and 0.7 for the crate. You're going to use the ramp to explore Newton's first law. That states that if the net force acting on an object is balanced, then it should either not move or move at a constant speed. You're going to try to let each object slide down the ramp at constant speed by adjusting the ramp. Specifically, you are gathering information that will help to determine the coefficient of friction of each object if you do have it slide down the ramp at constant speed. You're looking for an angle that allows an object to go down the ramp at constant speed or nearly so. Below the ramp angle slider is a go button. When you have an angle that you want to test, click on that button. If it goes racing down, accelerating, then you have got the angle too high. You need to reduce it some. By carefully adjusting the angle, you should be able to get a constant speed value for each object sliding down the ramp. On the left side of the display, there is a speed indicator and a time indicator. Adjust your angle so that the value of the speed does not change or does not change very much. Time is not important. What we want to do is keep the speed as constant as possible. This means that you have to experiment with different angles to make this happen. You will need to come up with some method, if you will, maybe increasing it by 5 degrees, maybe increasing it by 3 degrees, or whatever you need to do to get the object to travel down at constant speed. Once you have the angle set, then you can write the angle to that object in the lab write-up. You're going to come back to the simulation to answer one of the questions in the lab write-up, so you should not close it yet. But once you have those 3 angles found, then you're ready to do the analysis. If we apply Newton's first law to this problem, we need an incline at some arbitrary angle theta. Our goal is to find an expression for the coefficient of friction as it relates to the angle. So some sort of trigonometric function of the angle will be involved. Keeping this general, draw a box on the incline and identify all the forces that are acting on this box using a free body diagram. Friction always acts in the opposite direction of motion. The force of friction is defined in terms of the coefficient of friction and the normal force acting on the object by the incline. The normal force acts perpendicular to the surface of interaction between the incline and the object sliding down the incline, and it is at right angles to the direction of the force of friction. Finally, there is the weight, which acts straight down toward the center of the Earth, which is equal to the product of the mass and the acceleration due to gravity, g. Now you could use a traditional coordinate system straight up and sideways, but this would mean that you would be breaking up most of the force vectors into components that lie along either the horizontal or vertical directions. In the case of an inclined plane, you could rotate the coordinate system to lie along the incline and perpendicular to it. In this case, only the weight would have to be broken up into components, since the other two lie completely in the horizontal or vertical directions. This will be the x direction, and this can be the y direction. The direction up can be positive direction for our vectors, so that down would be negative. We can make the direction down the incline as positive because that is the direction of motion. The only requirement is that we stay consistent to our chosen system and the directions when we assign numerical signs to our vectors. Notice that of all the vectors represented in this coordinate system, that the weight does not lie in either the y or x direction. The weight is the only vector that will need to be broken into components of x and y in this coordinate system. One of the components would be along the y direction, down in the negative direction. The other component will be in what we have defined as the positive x direction. This one is going to be mg cosine of theta because it's adjacent to the angle, and this one is going to be the sine component because it's opposite the angle. The angle will be theta, the same angle as the incline, because it was necessary to rotate the coordinate system by that same angle to line it up parallel and perpendicular to the incline compared to the traditional orientation. If you were careful and kept the speed down the incline effectively constant, or not changing extremely much, then that means that Newton's first law, the sum of forces equals zero, applies. To properly apply this to a vector problem, it is necessary to separate horizontal vector forces from vertical vector forces. In other words, there will be two equations created from Newton's first law, one for those forces acting in the horizontal direction and one for those acting in the vertical direction. Perpendicular vectors are independent of each other, so this is justified. Collect all the horizontal vector forces to make a sum of vectors in the horizontal direction. Separately, collect all the vertical vector forces to make a sum of vectors in the vertical direction. Make sure to keep track of the signs that these vectors point to when summing them up. These two sums can then be set to zero to complete Newton's first law. There is no motion in the direction defined as vertical, so this justifies its application in that direction. And if the speed down the incline was effectively constant, then it is justified in the horizontal direction as well. In the x direction, there are two forces. There is the force of friction, which can be written as mu times the normal force, and it points in the negative direction. That means in the sum of forces, it is going to be listed as a negative vector. The other force in the horizontal direction is mg sine of theta, and it points in the positive direction. This means it is listed as a positive vector in the sum of forces in the horizontal direction. The sum of these forces can then be set equal to zero, assuming the speed in that direction is constant or nearly so. I have an equation that has mu in it. We want to be able to solve for mu, but it also has n in it. Both are unknowns. Remember, we are looking for an expression with the coefficient of friction set equal to some function of the angle, so for now it is unknown. That means that there are two unknowns in this one equation. You might recall in algebra, for those of you that took Math 150, that if there are two unknowns in an equation, it will be necessary to have two equations relating those unknowns in order to get a solution. Since the horizontal equation is complete, it is necessary to check if an equation created from the forces in the vertical can help. In the vertical direction, there are two forces, the normal force and the y component of the weight, and they are in opposite direction. The normal force points in the positive direction as defined, so it will be listed as a positive vector. The other component points in the negative direction, so it will be listed as a negative vector. The two can be summed, keeping their sign intact and set equal to zero. You might recall that one solution of two equations with two unknowns involves substitution of an expression for one of the variables into the other equation. Remember that the goal is to isolate the coefficient of friction on one side of our final formula and everything else, including a trig function, on the other. It will be necessary to simplify the trig function. One trig function to substitute an angle into is easier than two. There are trig identities on our textbook that can help with this, or you can search for trig identities on the internet. Make sure to end up with the simplest expression in terms of the trig function and any variables of interest that exist in the final expression. The steps for this proof should be put in your calculations page and included in the lab write-up you submit. So do this on a sheet of paper and photograph it and import that picture into the lab write-up after the last question. Once you get your relationship between the coefficient of friction and some angle function, then what you want to do is to put your three angles in and get a corresponding coefficient of friction for each of these angles. Put these results in the appropriate column in the data table. You are directed to get a percent error between the listed coefficient of friction and your calculated coefficient of friction. The percent error equation is the absolute value of the difference between the experimental and accepted value, divided by the accepted value, and finally multiply this calculation by 100 to get it into a percentage. Once you have calculated the percent error for each pair of coefficient of friction values, list the result in the data table. Only one example of this calculation needs to be shown in your calculations page. As has been shown in past analysis video, one should list the equation in variable form, then list the equation with the appropriate values put into the variables, and then list the final answer. Question number 1 asks you to predict something. Predictions in physics means use the physics applicable to the problem at hand and get an answer. In this case, apply Newton's first law to the problem presented, work through the steps, listing them in your calculations page, and come up with a force necessary to push a generic object up the incline at a specified angle. So force applied to do the job is on one side and all the other variables of interest in some form on the other. Put in the known values and get that force for the three objects, the file cabinet, the refrigerator, and the crate. Then you will do the problem using the simulation and get a result. Choose the angle that is specified and push each of the three objects, the filing cabinet, the refrigerator, and the crate, and see what force is needed to move it up the incline at constant speed. You will compare each of these applied forces to the three you predicted, getting a percent error between your predicted force and the applied force for each of the objects. You might want to collect these forces and the percent errors in a table like the data table for the angles, coefficient of friction values, and percent errors. So, in summary, this lab will have quite a bit in the calculation page section. There are 2 proofs that should be completed, and there are percent error calculations to be completed. Remember that in this case, you only have to provide the steps one time while putting all the other results using this equation in the appropriate tables. And your calculations page should follow the single answered question.